So if we have two molarity for this, we can't use the table anymore. We're going to have to do something else. But what physically would happen is, that's a solid, so that we have an excess of compared to that stuff that's dissolved. A higher amount of reactant means that the reaction is reactant heavy. And what that means is it's going to go to the right, because I want you to notice the arrow. The arrow is only a one-way arrow. So if you have a reactant heavy reaction, it's only one way, it's spontaneous in the direction it's written. That means that the reaction is going to have a higher voltage to the right. And you can think of it in terms of Le Chatelier's principle. I know Le Chatelier really is an equilibrium concept, but if you have a reactant heavy reaction and you know it's spontaneous in the forward direction, then it's going to cause the reaction to have more of a push to make products. And so that means a higher voltage. So if it's reactant heavy, it'll have a higher voltage than what was standard. And now on the contrary, if this is still 1 molarity, but the products are 2 molar, what would that do? Now this is the part that's a little bit harder to see. But I want you to recognize this arrow. Once again, the arrow shows the direction is spontaneous in the direction that it's written. So it is going to go to the right. But what happens when it's product heavy? Well, all that happens is it goes to the right, but there's a little resistance to it going to the right. But it still goes to the right. So that means that the voltage will be lower. So it still occurs, but with a lower push to the right and a lower voltage. So I need you to understand that conceptually. That's why I take the time in this slide. But then there is a way of calculating what the voltage will be. My plan is to derive that. However, I wanted you to see this before the end of the hour. So lucky you get out of the derivation. I'm just going to get to the end of it and tell you what the formula is. That's what you want anyway, I'm sure. You good on this? Arthur, I'll come back to it. Okay. But yeah, now I was going to show you how we got this. This comes from the Gibbs formula, and what we end up with is, because we have an expression for delta G now, it's negative NF epsilon. So if we rearrange things and do some substituting, we come up with, I want you to write this down, this equation in the box. The equation in the box allows us to calculate what the cell potential is. Notice there's no naught sign on it if we're not at standard conditions. You'd find the standard cell potential minus 0.0591 over n, same n, the number of moles of electrons transferred, times the log of Q. Q, remember, is products over reactant ratio. Now we'll start the hour using this tomorrow. I've got a couple of examples that we'll see how this thing works. The Nernst equation reflects what we wrote on the previous slide. The previous slide was all conceptual, but the Nernst equation mathematically is going to confirm when the voltage is higher and lower. So if you feel empty, like I gave you an equation without showing you how it's derived, stick around after class for a minute and I'll show you. Hey, you make me smile. Yes. Oh, go ahead. Yes, please. See you.